Hello everyone and welcome to this section. I'm super excited to discuss a very important topic in computer vision, which we'll call it Hough transform, okay? And we're actually going to use it directly, the Hough transform, along with what we learned before about region of interest masking, to actually kind of combine them together to come up with a technique that can detect lane lines for us, okay? So Hough transform mainly can be used to detect lines in an image, okay? And let's take a look at what do you mean by an actual Hough transform and how can we actually apply it when in an OpenCV environment. Okay, so a little bit of math. I know, like, again, I promised you not to cover or not to dig into a lot of theory and a lot of equations and mathematics, but I like, there's no way. I have to dig a little bit into the mathematics and show you how can we do it kind of a very high level into intuition form. So let's assume that I have this line, and my objective here is to model that line. Just get a model that basically tells me the equation of this line. We have covered that before in, in basic mathematics, that y equal mx plus b, where I can represent, any line as kind of giving me the slope, which is m delta y by delta x, okay, which is slope of my line, along with b, which is the intercept. How can I be intercepting the y-axis, okay? All right. Another representation, okay, or another kind of representation of that line using what we call it the rho value and theta. Okay, what do you mean? So let's assume that I have this line and here I have my origin. I can represent that as the exact same line using just kind of a different equation, okay? Assuming that from the origin, I'm gonna draw a perpendicular line to my desired line, okay? Again, this is my line that I'm looking for. I'm going to draw a perpendicular line to it, okay? I can represent the equation of this line using rho and theta parameters. Okay, what do you mean? So theta is simply the angle with the horizontal line. That's the theta. And rho is simply the distance from the origin perpendicular to the line, which is this distance. So I can represent this line using these two rho and theta parameters. Okay, it's kind of a different representation of the line. Why again, the question is an important question. Why are you teaching me this? I'm teaching you this because we're going to use them to actually kind of use these two parameters, okay, to obtain lines from the image. I'm going to show you how, which is very, very smart kind of technique. They're going to be used to detect lane lines within any image, or not lane lines, any straight lines. I'm going to use it again for self-driving cars to detect the lane lines. All right. So again, rho is the perpendicular distance from the origin to the line, and theta is the angle formed by this perpendicular line with the horizontal axis, from this perpendicular line to the horizontal axis. And this is simply the equation of the straight line, the exact same straight line. I can x multiplied by cosine theta plus y times sine theta. That will give me the rho value. And that's kind of the two equations of a straight line, exact same straight line. All right, let's make use of what we learn. All right, so let's assume that I have my vehicle, and I'm taking a camera image from this vehicle. Okay, what I'm looking for is that I'm looking for the equation, or I'm searching for the line. In order to search for the line, I need to search for the equation of that line. So again, I mentioned the equation of any line, not specifically lane line, just any line, is y equals to mx plus b, or x cosine theta plus y sine theta equals to rho. Okay. All right, so these, in simply put, what we have just described is what we call it in the image space. So in the actual image, I can represent the equation of the line using one of these two equations, okay? However, instead of using the image space, I'm gonna use what we call it Hough space, which is a different kind of representation of space, okay? What do you mean? So each line in the image space, so this line in the image space, we're gonna be represented by a dot in what we call it Hough space here, okay? All right. Simply put, in the Hough space, I'm going to put here my m, which is the slope of the lines, of all lines. Here I'm going to put the b, which is again the intercept with the y-axis. And each of the line, again I mentioned, this line can be represented by y equal mx plus b. So it has specific slope and a specific intercept with the y-axis, m node and b node. Simply put, I can take this and put it in the Hough space as just one dot. Again, this dot represents a straight line, which is m and b, okay? In the same fashion, I can represent in the Hough space, again using this equation, I can represent the exact same point using what we call it rho and theta parameters, or rho and theta values. All right. Again, why are you teaching me this? Why are we going from, like an image space, so we'll call it Hough space, okay? The whole idea is that I wanted kind of to scan my image space. That's the whole intuition, okay? I'm gonna show you all the details in the next slide. But the whole idea is I need to look for a line, okay? So in order to look for that line, what I'm gonna do, I'm gonna kind of scan the entire image in a way, and each time or each of the points, I will try to get, rho and theta for these different points. So along the point, along whatever points, I'm gonna get rho and theta. Again, rho and theta, or M and B all the time, okay? And I'm gonna draw that here in what we call it my Hough space. So simply in the Hough space, I'm gonna be drawing all the representing the entire image in what we call it M and B coordinates, or rho and theta coordinates, all right? And simply put, we're gonna do what we call kind of a voting exercise. In simple forms, every time you're gonna be doing, a transformation from an image space to a Hough space, you will see kind of the M and B has been repeated several times, which kind of a voting way, which is kind of an accumulator. It's kind of in this point, which is indicating M and B or rho and theta, you will see that there is kind of, like an accumulator that shows, okay, there's like 80 points, or let's say 100 points, which means that's kind of a vote that tells you, okay, maybe this point has a line in it when you shift from here back to the image space, okay? If it's not clear, I'm gonna show you an exact example moving forward, but that's the whole idea of why do we actually move from an image space to what we call it Hough space, okay? Simply put, I'm gonna represent every line in the image space by a dot in the Hough space, okay? Again, this dot can be M and B or can be rho and theta. Let's again take another look, an actual practical example. Let's assume that I have this image, which is again pure white image, with two lines, horizontal lines in it, a blue line and a yellow line, okay? And this image is 100 by 100 image with horizontal line in the middle. I try to include the details here as much as possible, again, to avoid any confusion. It's a little bit confusing at first, but once we run it, you will see it's very easy. First, we're gonna create what we call a 2D matrix. So we're gonna create a matrix, okay, that has all the rows and all the thetas, all right? Kind of all the rows here and all the thetas in here, okay? And we'll set all of it to zeros. So simply put, we don't know where the line is. We're just gonna create a matrix and set 0 into it. All right, first step, I'm gonna select the first point on the line. So let's assume they're gonna select the first point here on that line, okay? So for each point, what I'm going to do is that I'm going to kind of scan the entire angles, entire theta, okay? So we're gonna do a rotation from, let's say 0, 1, 2, and so on up until, let's say 180, okay? So we're gonna try simply different values of theta, all right? And for each value, I'm gonna obtain the rho back again, all right? So again, simply put, here I have this equation. I know this point, so I know x and I know y. And what I'm gonna do is I'm gonna try different values of theta. I'm gonna try theta of 1. So here I have all the values here are known. However, rho is unknown. So basically, I'm gonna substitute in this equation, get rho value, all right? All right, which means at this point, I'm gonna get rho and theta, all right? I'm gonna put it here in this matrix, okay? And then the next step, what I'm gonna do is, for every rho and theta pair, what I'm gonna do is I'm gonna go, let's say, to the next point, all right? And do the exact same exercise again and come again with rho and theta values. I'm gonna come to the next point as well and do again the exact same exercise, rho and theta values. So you guys can see here, simply put, the rho and theta value, which is here, we're gonna be 50 and 90, all right? Again, it's a little bit confusing, but bear in mind, so bear with me. So 50 and 90 indicates that, okay, rho, which is again distance from the origin, it's in the center exactly. So here the distance is 50, and the angle is 90, right? Which is the angle from the origin to the line is 90 degrees. And that's why you will see in that specific cell, which is 50 and 90, okay, every time I'm gonna be incrementing it by 1, all right? So again, as you move forward, for example, this line, you will see that every time all the points here on the line have a 50 and 90 rho and theta, all right? All of these points have 50 and 90. Every time you draw a perpendicular line from the origin to that line, you're gonna get the exact same value. it's at the same distance 50 and have this exact same angle 90. Simply put, every time you're gonna move to this line, you're gonna kind of increase the accumulator within that value here by 1. So here you're increasing it by 1, 1, 1, 1, which means simply when you go to the Hough space, when you see a point in the Hough space that has a lot of values, the accumulator is very high, it's a very large number, that indicates that a line has been found in a very simple form, okay? All right? So simply put, this line is represented the Hough transform as just one dot, okay, indicating a lot of intersecting simply points or a lot of accumulators, just kind of, you know, like a lot of values within that grid that we created out of 0, out of nothing, okay? So simply put, cell 50 and 90 will be voted up. The accumulator with maximum votes simply indicates a line. So a line has been indicated or detected in the image. All right, what about the yellow line? So this line has this exact same angle. So you guys can see that theta is the same, so 90 is the same. However, the distance from the origin is around, here we set it to 25, pretty much. Okay, so the distance from here to here is around 25. The distance from here to the blue line is 50. And that's why you would see here, if we have two lines, you would see that this accumulator has been accumulated as well, increased as well, indicating there's another line at 2590 location. Okay, again, it's kind of a different representation of the exact same thing in what we call it an Hough transform as opposed to the image transform. Okay, all right. So what I'm gonna do with this, simply put, I'm gonna apply kind of, you know, like find Hough lines, okay, kind of a function we're gonna be using within OpenCV that can gives me exactly what are the rho and thetas of all the lines that have been found in the image. It's really powerful, it's really intuitive, and it's going to be used to detect lane lines within an image. All right. Okay. So how can we apply it? I'm going to actually use again cv2.houghlines. I'm going to provide it with the image. I'm going to provide it with these parameters. I'm going to provide it with rho accuracy, theta accuracy, and threshold value. Simply put, here I'm going to define in general. Let's assume I'm going to put, let's say, 1 and pi divided by 180, which means 1 degrees, and then 240. That will kind of create our resolution, all right? So the resolution within the parameter rho, how many pixels, I'm gonna need my resolution within the parameter rho. I need theta, which is my resolution of how many angles I'm gonna be doing. You guys remember we had a grid, okay? That indicates the grid here. How many times I'm gonna be evaluating and rotating every 1 degree, every 2 degrees, and so on, all right? And that's the kind of the values gonna be doing rho, theta, and the threshold as well. Threshold, which is kind of, you know, the vote. If you guys remember, every time we increase the accumulator, that's kind of, you know, the vote. How many times do I need to include? If I put, let's say, 240, that's kind of the minimum vote that I need to detect, okay, that's a line. That's a flag that tells me, okay, I found the line. That's kind of the minimum threshold that I need, okay? All right. And simply put, cv2.houghlines will gonna give me or return all the lines that has been found in the image, which is amazing because now I can basically select which line is perfect. I can know the slope. I can then center my vehicle. I can do wonders with it moving forward after we detect the lines within the image. All right, and that's pretty much all I have for this section. I hope you guys enjoyed it. And now to the fun part and actually implement it within the Python environment. And then afterwards, what we're gonna do, we're gonna combine the region of interest masking along with the Hough transformation to actually detect a lane line within an image. I hope you guys enjoyed it and see you in the next section. Hello everyone and welcome to this section. In this section, we're going to apply Hough transformation to actually obtain the line within an image. Again, we're not gonna go directly into detecting lanes. Here we're just gonna detect lines within any image. We're gonna try very basic images, you know, kind of a calendar, which is have, you know, kind of vertical and horizontal lines. What I'm going to do is I'm going to try to extract these lines out of the image and actually detect it, kind of, you know, mark them with a yellow color or blue color or whatever color we want. All right, let's get started. First of all, we're going to run, import all our libraries, and then we're going to have an image, we call it horizontal vertical, which is a simple image that has simply a horizontal line and a vertical line, okay? And so let's take a look. So this is the image that we have. Again, this kind of very simple image has this horizontal line and this vertical line. My objective is I'm asking OpenCV to actually extract these lines, to give me these two lines, all right? Okay. All right, let's show this. So here you guys can see the pixels around 350, give or take. And here we have around 450, okay? All right. The first step is we're gonna convert from colored to gray, and then I'm gonna apply canny edge detection. I hope you guys remember canny edge detection. We have performed that before. The whole idea is in order to perform and actually apply our Hough lines application, it's better that we get a gray image and then get a canny or edge detected image. It's going to make your life way easier. Actually, kind of a recommended practice to perform. All right. So again, if you guys recall, here we convert again from BGR to gray. That will give me the image gray. And then I take the image gray, and then I'm going to apply canny, cv2.canny, to actually obtain my image canny, which is kind of the canny edge detection on the image. All right. Okay. So here we run it, and then let's show the actual image. So that's it. That's my image. Again, that's image after we obtain the edge detection. Again, it's showing kind of the lines, and that's the first step. All right. Okay, great. Let's exit that part. And then the next step is I'm going to apply cv2.houghlines. Okay, and then I'm going to give it the argument going to be my image canny. And then here I'm going to define the resolution. So here I'm defining the resolution of row parameter. Here I'm defining the resolution of the angle, which is again, here I'm defining pi divided by 180, which is 1 degrees, pretty much. And then here I'm going to define simply the threshold, which is kind of the voting. What's the minimum number of votes that I need to include in order to actually detect a line? All right, let's run it. And that's pretty much it. In lines in here, we're going to return simply all the values, which is rho and theta for all the lines that has been detected. All right, so what do we mean by these numbers? Okay, so first of all, this is simply the rho parameter, and this is my angle, okay? But the angle here is in radians. Again, I don't want you to be confused. Simply put, 1.57 radians is actually 90 degrees, which makes sense, that you have two lines at 90 degrees, which is simply these two vertical lines, right? And then you have another two lines at 0 degrees, which is kind of the two horizontal lines, all right? And that's kind of the rho and theta parameters, the rho and theta values that you obtained. And here it shows you the rho parameters, which is the distance from the origin, okay? So again, 170, 170 around, which is pretty much here, which makes sense, 170 and 170 around. And then here, the distance from the origin is around 220 for these two kind of vertical lines, which is again 220 approximately, okay? Which makes, again, complete sense. All right? Okay, sounds great. Actually looks like it has been working fine. Here, we're gonna do length of lines. We're gonna detect 4 lines. Again, why 4 lines? Because each of these two, because when we perform canny edge detection, it actually showed us kind of, these are kind of 2 lines, and here I have 2 lines as well, all right? Okay, looks great. All right, and then we're gonna do lines with shape. That would show me the shape of the lines. And what I'm gonna be doing here, simply put, I'm just gonna be going there, okay, and trying to plot these lines, okay? So what I'm gonna do is gonna simply create 2 for loops, all right? Every time I'm gonna getting these parameters, which is lines. Again, I'm going to 0 and 0 and 0 and 1, indicating my rho value and theta value. And simply put here, this kind of simple conversion to provide, instead of providing rho and theta, which is I can plot in OpenCV, what I could do, and I can use cv2.line, okay, to actually plot the line. But what I need, the coordinates of the starting point and the end point of each line. And that's pretty much what we obtained here. Again, it's a little bit of math. Again, if you're not interested, just skip it. And simply put, we're just conversion from rho and theta back to x1, x2, or x1, y1, my apologies, and x2, y2, okay? That's pretty much all the coordinates here of x1, y1, x2, y2, which is simply the start and end point of the line. So I can just use cv2.line to actually plot my lines. All right, let's run it, and that's pretty much it. Actually, you guys can see here the blue this has been indicating that we actually detected already in our 4 lines. If you guys can see in between here, kind of it shows black. Why? Because when we perform the canny edge detection, it actually removed what the actual value within the lines, right? Just get the edges of the line. And these are the lines that have been detected by the Hough lines, all right? Okay, sounds great. Let's take a look at another image. Instead of this kind of simple image, what I'm gonna do is I'm going to apply it to kind of a calendar, which is another image, all right? So here I have my image, just a very simple calendar. And you guys can see that I have lots of vertical lines, a lot of horizontal lines. Okay, let's actually show the image. Let's run the pretty much the exact same thing. So here I'm showing the image again. All right, here I'm getting the canny. Let's show the canny. So here you guys can see the canny edge detection. All right, let's exit this part. Let's apply the Hough lines. Let's get the lines. Obviously here the lines are more than before. But again, pretty much all of them are vertical, 1.57, which makes sense. And zeros, which is horizontal, which makes sense. Okay, go down, down, down. All right, which looks great. So now you guys can see we have been able to detect all the lines, simply put, by just using the Hough lines function within OpenCV. All right, and now we are pretty much ready to combine all the learnings we have done so far to detect lane lines within an image. All right. I hope you guys enjoyed that section, and I can't wait to discuss the next section with you. Thank you, and see you in the next section. Hello, everyone, and welcome to this section. In this section, we're going to apply the region of interest masking that we have done before, along with the Hough lines transformation, to actually detect lane lines within an image. Okay. All right. Let's get started. So let's run the first section, just importing all the libraries, and then here we're gonna show the image. So this is kind of, like a very simple image, and my objective here is to detect these two lines within an image, okay? All right. First step is that we're gonna take the image and we're gonna convert the image into grayscale. Again, we have done that several times before. I hope you guys are experts by now. So I took the image C, which is image color. I'm gonna apply color underscore BG RGB to gray, and that will gonna simply obtain the image in grayscale. And let's plot it. Let's see what it looks like. So that's again my image in a grayscale, and if you guys can see, the dimensions of a colored image is 540 by 956, and it's 3 dimensions. And here we have 540 by 956, which means just a single kind of dimension, which makes sense because it's a grayscale image. All right. The next step is we're gonna do a canny edge detection, but before canny, what I'm gonna do is we're gonna do Gaussian blurring. We're just gonna take the image, blur it a little bit. All right, and then I'm gonna apply canny on it afterwards. So what I'm gonna do is I'm gonna use OpenCV cv2.Gaussian blur. I'm gonna provide the image along with the dimensions of my kernel. Okay, which again just gonna use 7 and 7. You guys can again try all these parameters are adjustable. You can get better or worse result than this. Okay, that will return the image blurred, and then here we're gonna plot the blurred image. Let's run it. And you guys can see here, the image is a little bit blurred. Again, it doesn't show, it's showing here as kind of, like colors because I didn't show the color map. Okay, here if you specify color map as gray, it will show the grayscale image. Okay, all right. The next step, I'm gonna apply again canny edge detection. Again, you guys are experts by now, cv2.canny. And then gonna do the image blurred, that's my image. I'm gonna apply the threshold. So I'm gonna define the threshold low and threshold high to indicate, like 10 or 200, for example, just indicating the threshold values. Okay, and then I'm gonna plot the image canny afterwards. Let's run it. All right, and that's my image in a kind of a canny form, which kind of edge detected form. As you guys can see here, these are kind of my 2 lanes that I'm looking for. And obviously I'm not looking for any of this. I'm not interested in looking for the lane lines in the sky or here in the back, with all the trees and so on. So I need to get rid of this. I want to get rid of even this because, it's a lane, yes, but it's kind of outside my region of interest, okay? All right. The next step is going to define my region of interest. Again, we have done that before. Let's take a look. So here I define my vertices, as this, which is simply, I'm going to pick, first of all, I'm going to pick a couple of points. First, I'm going to pick point 20 and 460, which is indicating my the value of here. I'm just gonna go to, let's say, around 20. I'm gonna go down to around 460 approximately. So it's just gonna be somewhere in here, okay? And then I'm gonna select 340 and 300, which is again, I'm gonna go again 340, which is somewhere in here per se, and 300, which is this point approximately, which again, I'm gonna be selecting, like this region. Obviously, I'm going to have another point which is have the same y-axis, which is pretty much the same this. That's why there's 300 and 300, because these 2 points have the same y value, but it has different x. It's shifting in the x direction. And that's why you would see the x is around 450, 460 approximately this point. And then I'm going to select the last point, which is somewhere in here. I'm going to select 740, which is again 740 and 460 going down, which is kind of this fourth point. And that's pretty much my region of interest that I'm interested in. I'm going to skip anything else. I'm not interested in any of them. Okay, that's the first step. Second step, I'm going to create a black image. And that's why I'm going to call again numpy.zeros_like. I'm going to use image gray just to get the dimensionality of my image. I'm going to create a mask. All right, if you guys recall, this is a mask with all zeros. What I'm going to do is I'm going to define in my region of interest that I defined. Okay, I'm just going to set it, put ones in it, just define, you know, like bright colors in it or light or white color in it. So I'm going to use my mask. I'm going to use the command cv2.fillPoly, fill polynomial. I'm going to define my vertices, which is I've had here. I'm going to put 255 indicating number 1 or white colors within the region of interest. Perfect. Afterwards, I'm going to take my image, which is my original image, or a grayscale image. I'm going to use my mask, which has, again, all zeros and some ones in here. Do bitwise ending that will specify or indicate my region of interest. Okay, which is, again, my masked image. All right, then I'm going to show my masked image. Let's run it. All right, and it looks perfect. You guys, again, can try different points. You guys can, if you want to extend the region of interest to make it, for example, here between this corner and this corner, you can do it. But this kind of, you know, like the lane is a little bit shifted. That's why it's very difficult to just go from here to here. You can still do it, obviously. But again, the image is kind of a little bit tilted or shifted to the left. All right. And then afterwards, what we're going to do here is we're going to do masking between the image canny and the mask. All right, let's run it. And that will show me pretty much what's left, not from the original image, but actually from the canny values. So that's pretty much what I'm looking for. If you guys recall, this pretty much looks exactly the same as we had before when we were detecting lines using Hough lines in a simple calendar, if you guys recall from previous sections, or in just that simple image that has a vertical and horizontal line. Okay, that's pretty much all what I need. Okay, so what I could do moving forward, I was just going to use my Hough lines. Okay, to simply detect all the lines. So I'm going to use cv2.houghLines, but here I'm going to use what we call probabilistic Hough lines. Okay, that's why I use Hough lines P. Okay, again, it's I'm not going to dig into the mathematics of it, but the whole idea is just going to give me like kind of a vector that with lines in it, which is instead of using cv2.houghLines, I'm going to use houghLines.p, which is kind of probabilistic form. Okay, you guys can read into it a little bit more if you wanted to get, but here we're just going to use it to detect or indicate all the lines within the image. All right, so here I'm going to define some parameters here, rho, which is the distance, resolutions, and pixels. I'm going to define the theta. If you guys remember how many times we're going to be rotating, here I'm going to be rotating angular resolution of 1. Again, the threshold, which is the minimum number of votes, I'm going to set it to 40. You guys, again, all these are tunable parameters. Here I'm going to define the minimum line length, which is the minimum number of pixels to indicate a line, which is 100, and maximum line gap, which is 50. Which is simply maximum gap in pixels between connecting line segments. All right. Okay. Let's run it, and then what we're gonna get here out of this is gonna get lines, and then what I'm gonna do here, I'm gonna create again an empty image. Okay, we'll call it line image, and what I'm gonna do is I'm gonna take the empty image and draw all the lines on it in a simple form. So what I'm gonna do, I'm gonna create a for loop. Okay, we're just gonna call it for line in lines again. Lines is simply the number of lines or the actual indices of the line. Again, x, the different points, the start and ending point of all the lines that has been detected within an image. Okay. All right. So what I'm going to do is I'm going to create again this for loop to loop on all lines, and then every time we're just going to go and grab x1, y1, x2, and y2 within my line, which is I grabbed here within the previous for loop. And every time we're just going to go take my line image, which is kind of a blank image, and put all these points in there. Put the point start point, put the end point, and afterwards I'm going to put the color. And here I'm going to simply specify the color, which is here I'm going to specify like a green, red, or whatever color we want it. Okay, and then afterwards we're going to return the lines. This is simply we're going to just create on the line image, which is again blank image. I'm going to draw all the lines that I've had before. Okay. All right, let's run it. And here I just wanted to show the lines as well. That's why I indicated as well. I tried to plot the lines, which is just show us, okay, it has been detected around 6 lines in here, showing all the start and ending point of all of them. Lastly, I'm just gonna simply take the image, okay, or the image, which is again blank image with all the lines on it. I'm just gonna put it on my image, which is on my original image. Simply put, just to show my lanes, and if we're gonna detect, for example, 2 red lines or something, that will indicate my lanes, just like for display purposes. So I'm gonna use cv2.add weighted, okay, which is again very simple technique that you can just use within OpenCV. We're gonna provide image C, which is again my original image, which is on top here. That's my image colored, okay, which is this image. I'm just gonna take it. All right, and then what I'm going to do is I'm going to again use alpha. I'm going to use my line image, which is the image with the lines on top drawn. I'm going to use beta and use gamma. What are these values? Here I try to include the equations just for you guys to understand what's happening. Simply put, I'm just going to use the original image multiplied by a specific factor. And then I'm going to use my second image, which is the line images multiplied by a certain factor. And then I'm going to use gamma value kind of, like as a factor to add or subtract values from the pixels. Simply put, I'm just merging these 2 images together, and then I'm going to plot it after. Let's run it, and let's run it, and that's it. Very interesting. So that's pretty much, if you guys can see on my image, now I can detect specific lanes within my image. If you guys can see, it looks pretty interesting. And you guys again can go up here. You can change, you can change any of these parameters and see if you can detect, lines more accurately. You can detect maybe shorter line. Maybe you can increase the region of interest and try to detect this line, for example. And then, obviously, what you could do moving forward, you can use this image instead of actually having an image. You can put all of what we have written here in a function, okay, and use. Kind of instead of applying a photo here, you can use a video stream, which is pretty much the same, exact same idea. Video stream is simply just one series of images. So we're gonna take all this, put it in a function, and simply call it several times. Every time, take an image and send it to the function and draw lines. Go back and keep doing this, kind of what we call it pipeline. Then you can develop your own pipeline to actually run it in real time if you wanted to know or indicate where your lane is. Once you know your lane, then you can center your vehicle, and then you can start to detect objects moving forward. We're going to cover that moving forward. We can detect traffic signs and so on and so forth. All right. I hope you guys enjoyed that fun project. I hope you guys enjoyed it, and see you in the next